Okay, this is exam 3 going over the solutions. Number 1, we have 2 balls chosen randomly from an urn, and I think I added in that they're not being replaced. So choose one and then choose a second without putting the first back in. 6 white, 2 black, 2 orange, $2 for each black, lose 1 white for lose $1 for each white. X is our winnings, and just to clarify, winnings means the total amount that you're winning or losing. So winnings could be a negative number. What are the expected value of X and the variance of X? So we have 6 different situations here. You might map it out by this is how much you could win on the first ball, how much you could win on the second ball, and then kind of matching them up to see all the different ways that would work out. But there are six different solutions. And we have to look at the probability of getting each of those. So let's take one, for example, x equals -2. The only way we would lose $2 is if we drew a white each time. So drawing a white the first time is a 6 in 10 chance. Then there's only 9 balls left, 5 of which are white, so 5/9, multiply it out to get 30/90. Another thing we could do is we could choose 6 choose 2 over 10 choose 2. Either way should work out fine. And then notice, so it's pretty straightforward after there. Notice though that on x equals -1, there's 2 different ways that could happen. We could get the white, then we'd have to get a neutral, so an orange, or an orange, then a white. Or you could just do it once and then multiply by 2. And we're going to have 3 different situations where that's the case, where we have that 2 possibilities. However, if you forgot it, so for example, I forgot this x equals 2. I just thought, I don't know why I forgot that the first time around. But when I added up the probabilities here, remember they should equal 1, because this is the entire range of x's that are possible, and add up their probabilities, it should sum to 1. So when I summed it up, I noticed I was a little bit off, so then I went back and checked until I found that I had overlooked one of these right here. So add those up, they should equal 1. Expected value, you're taking the probability of each one times the actual value here. Notice all of them, I had a denominator of 90. You could actually have 45, would be even better, or more reduced. So I just pulled out that 1/90th, and then this is -2 coming from this value, and this is really 30 over 90 because it's the probability of getting the -2. So we add all those up, simplify it out, and we get -40 cents. So on average, for example, if I played 10 games, my best guess of how much I would lose or win would be losing $4. So on average, I'm going to lose 40 cents a game. Now when I get the variance, I need to get this expected value of x squared. So very similar. The only thing is these x's here all get squared. Notice that the 0 doesn't even appear in this because it'll get canceled out when we take 2/90 times 0. That'll just end up being 0 anyway. So my expected value of x squared is this, variance of x, and subtract them out. I think it's 2 point something there. So how would I check if this is reasonable answer? Well, first of all, I should check to make sure I have a total probability of 1. Second of all, losing about 40 cents makes sense because I'm slightly more likely to win than lose if there were the same amount of blacks and whites, but there's 2 blacks and 6 whites. So one way you can think of it is on any given draw, there'd be $4 of winning balls in there, $2 times 2, and $6 of losings, potential losings, 6 times -1. So the losings, from that perspective, are going to outweigh the wins. And again, I'm just doing this real loosely to check and see if this makes sense. So it's pretty close, but a little more towards the losing side. So minus 40 cents, a loss of 40 cents on average does seem about reasonable. Variance, it's a lot harder to check really what a good estimate is, but that mean I should be able to check. Okay, we have two independent flips of a coin. I originally did three, and I wanted to reduce the burden on calculations and everything. So we have three possibilities for x, either 0, 1, or 2 heads. So x minus 1, which is just a function of x. In other words, each of the values gets 1 taken away from it. So these are the three possibilities. Notice it is possible to have a negative value for one of your random variable outcomes. In fact, even if we had our original random variable, not in this case, but there certainly are other cases where this could take a negative number. What you can't have negative is the actual probability of any of these values. Okay, so we notice that probability of x equals 0 corresponds with probability of x equals 1, which in both cases is 1/4, and same as x minus 1 equals 1, whereas the x equals 1 picks up the other half. Again, we should be able to add these up, 1/4, 1/4, 1/2, to get 1, so we know that the total probability equals 1. Plotting it, we have the PMF, so that's the probability of getting each particular of whatever our random variable is, which in this case is x minus 1. So this anything here on the axis represents the value of x minus 1, and then on the y represents the probability of getting that particular x minus 1. Okay, we have 1 through 30, 30 different balls. We're going to select 5 balls. Key point here, replacing the ball before drawing again. And x is going to be our highest number. So probability x equals 1. In other words, all 5 balls must be a 1. So 1 out of 30 chance times 5 to the 5th power, because we need to do that 5 times in a row. People did pretty good on part A. Part B is where it got a little trickier. So we have a fairly easy to calculate x is less than or equal to 7 because we'd have 7 options. Now the reason we can't just take 7/30ths to the 5th is because even if we have all 7 options available to us each time, we might get something between 1 and 6 every time. In other words, we might not actually get the 7. And the problem with that is, in order for x to equal 7, we do need to get at least one 7 in there. We also can't just take one of the 7s and say 1/30th and then the rest 6/30ths, because we might have more than one 7. And we can't just take 1/30th times 7/30ths to the 4th. We can't just say, okay, let this be our 7 and then get 4 other balls that could be 7 or not, because that's going to include duplicates. So 2 ways to do it. One is x is less than or equal to 7, and then subtract out exactly the part we don't want, which is x is less than or equal to 6. So that leaves us with x equals 7. So certainly we could do that. Another way that I thought was really neat that some students did was just going through and calculating the 5 different cases. In other words, you get 1 7, 2 7, 3, 4, 5 7s. Those are the only 5 cases where x would equal 7. And of course, all the other balls were between 1 and 6 then. And there's no overlap there. There's no duplicates because all 5 cases are mutually exclusive. So how would I check this number? Well, I know that this should be really small. X equals 7. I know it should probably be larger than this because I have some freedom in some of the balls that I can get. But it still would be a pretty low chance, you would think. Roughly 1/30th, although that would of course need adjusted, but because not each of the 30 are going to be equally likely here. But this does seem like a reasonable, and it's certainly positive. Some people had negative answers. For a probability, remember that you should always be between 0 and 1. Okay, this was actually the best one on the exam, I think, because it was a fairly straightforward problem if you recognize that it's Poisson. So we have 2.5 hurricanes hit a region in a year on average. So probability there will be no hurricanes. So we're looking at year as our unit here on part A. So in the first year, if we have probability x equals 0, It's just a Poisson with lambda equals 2.5. So plugging that into the PMF for Poisson, you'd get e to the negative 2.5 times 2.5 to the 0th over 0 factorial. But of course, we know that when x equals 0, all of this just cancels out, and we have this here. For the second one, we could do it two ways. We could change our unit, so instead of looking in terms of every year, we're looking in terms of every 2 years, in which case our lambda would then be 5, and we would just be looking for probability x equals 0. Oh, I guess I have it written out here. Would just be e to the negative lambda, or e to the negative 5. Another way we could do it is split it into first year and second year. So now we're looking in terms of each year. So notice that we get to decide what our interval is. And in that case, getting 0 this year, getting 0 this year, they're independent. We're assuming they're independent. We multiply those out to get e to the negative 5th. Okay, so how many times would you have to roll a 6-sided die before you had gotten all 6 values? We could do this a few different ways. One is, let's create 6 different random variables. Now we don't want to do x1 equals how many times do we roll until we get a 1, x2, how many times do we roll until we get a 2, and 3, because that makes it very complicated when we go to do the calculations. Sure, we could do the expected value of x1 if x1 was number of times until we get our first 1. Of course, that would be a geometric with p equals 1/6, so that would be 6. And expected value of x2 would be 6. Again, this is not how I'm setting it up here. If x1 were times until rolling a 1, the problem is when we go to combine them then, we would have to assume independence, and really we need a conditional. We want, and it would get tricky because we don't even know which order we're rolling the numbers in. So a neater way to do that, neater as in cleaner way to do that, is let x1 the times you roll until you get the first unique value. In other words, a number that you haven't yet rolled before. And so on down to x6th, where you get the last value that you haven't yet gotten. Okay, so how many times would we have to roll it before we get our first unique value? Well, this we can do even without thinking too much. Of course, we could do a geometric distribution, but it's pretty clear whatever you roll in the first roll will be a new number. And again, this is pretty much exactly the same situation as the collecting the 5 frozen characters, Olaf and Anna, Elsa, so on. Except in this case, we have 6 different values we're trying to hit. So getting the second value then, notice that our p is now 5/6, because the only one we can't get is the one that we've already gotten, but 5/6 are still available to us. Expected value of a geometric distribution with 5/6p is 1 over 5/6, in other words, 1.2. So on, so the third unique value, we'd have a 2/3 chance of getting something unique, a 1/3 or 2/6 chance of getting something we already have. So our p is 4/6. 1 over 4/6 gives us 6/4 or 1.5. When we get all the way down to here, this was the exit slip question with Olaf, basically. So we've already gotten the other 5. We just need to get the last one now. But now we only have a 1/6 chance of success, because all of these others would be duplicates. So geometric with p 1/6 is 1 over 1/6, or 6. Add them up, you get 14.7 rolls. Is this reasonable? Well, for the wrong answers, most people had either 6 or 36. 6 should not be reasonable, because we wouldn't expect to, the first 6 times that we roll the dice, we wouldn't expect to get 6 different numbers, because that would be a very rare event to actually be able to not get any duplicates on rolling all 6 dice. It'd be like rolling 6 dice all at once and not having any number the same, getting kind of like a straight in Yahtzee, which would be very difficult. And 36 also, we know that the expected value to get the last one is 6, so 36 seems too high.